So good afternoon to all. I'm going to show you my work on compressed sensing reconstruction of 3D ultrasound images using line-wise sampling and dictionary learning. So this is an experimental study because the simulation study has already been validated. So we interest ourselves only in 3D ultrasound images. And in 3D ultrasound, there are basically two big types of acquisition systems. So you have the mechanical scanning system, which is represented A, B, and C. And in these cases, you use a 1D transducer, you swap the volume to motion. And the downside is that the transducer here is kind of heavy, bulky, and can be inconvenient of use depending on the position of the part of the body that you want to image. And it requires a large number of ultrasound lines, and the frame rate is quite average of only 2 or 3 volumes per second. And then there's a second type of system here in D, which is a scanning system that is using 2D arrays. So the transducer is a 2D phased array matrix. So the swap of the volume is done electronically, and you get real-time 3D images. However, the downside here is that the challenge of connecting all the piezoelectric elements and activating them in reception and emission. So it is to this type of imaging 3D ultrasound scanning system that we want to apply the compressed sensing theory. So I'm going to briefly present you the compressed sensing theory because everybody has its own notations. So this compressed sensing offers the possibility of acquiring compressed data. So that means a simultaneous signal acquisition and compression. And the figure here shows a summary of how a compressed sensing works. So for example, if X is the signal that you want to reconstruct, it has N samples. Then on the left side, you have the acquisition part of the compressed sensing, so the sensing part. And on the right side, you have the compression part in red. So if you look at the acquisition part of the compressed sensing, first of all, you need a projection of your vector X. So this depends on the acquisition system. So for example, in MRI, it would be the Fourier basis, and in ultrasound is the Dirac basis. So what you actually acquire is Y here, which is subsample and has a lot less measurements than X. So M is a lot smaller than N. And then if you look at the compression side, so you want X to be S sparse in a sparsifying basis psi, where S is the number of non-zero coefficients, and S has to be very, very, very small. So for the sparsifying basis, there are two options. You can either have a fixed basis, where like Fourier, DCT, wave atoms, and others, that represents well your signals, so for in our case, the ultrasound signals, or you can have a dictionary that you learn from the data. And we will see this later on. And in summary, the mathematical formulation is quite straightforward. And for the sparsity hypothesis given here by equation 1, well, X is sparse in psi. And then the linear measurements part is given in third equation and depends, or the vector of measurements that we acquire depends on R, which is a random subsampling matrix, and on phi, which is the acquisition matrix, and it will be the drug. And V are the sparse coefficients, the vector of sparse coefficients. So we interested ourselves in learning sparsifying dictionaries, because in this case, C will be a dictionary that will be optimal, and that this will best sparsify the family of signals that interest us. So the dictionary learning problem is given here, and X is our training sample. So this will be patches coming from different volumes and different types of organs of 3D ultrasound volumes. And this is our dictionary composed of K atoms, where one atom is on each column. And then theta is our matrix of sparse coefficients. So this is a minimization problem that depends on the sparsifying sparse constraint here, and where we optimize in function of two coefficients, D and theta. So this is an NP-hard problem that we chose to solve through the K-SVD method, which iterates between these two main steps. So first you have the sparse coding step, where you fix the dictionary and you solve the minimization problem in function of this and find the sparse coefficients. And once you have the sparse coefficients, you go on to the dictionary update stage, where you update your dictionary one atom at a time, using only those examples that use it from the training samples, and you fix the non-zero support. For example, if this is a DCT at initialization, and if we apply the K-SVD method on ultrasound images of different organs, then at the end, at convergence, you will get a dictionary that is completely different than the initial one. And in the case of ultrasound signals, well, the texture in every patch atom changes from one to another. So compressed sensing, however, has already been applied to ultrasound imaging. So from a sparsity point of view, some authors consider that the scatter map was sparse, and others consider that the radio frequency signal are sparse, either before the raw RF signals or after beamforming, so the beamformed RF signals. So these hypotheses were done in fixed sparsifying basis. And from a measurements point of view, then you have the digital-to-digital approaches, where the projection of the acquired vectors were done on Gaussian or Bernoulli random vectors. Then you have the analog-to-digital approaches that were also extended to 3D. And there is an approach that directly samples the entire radio frequency lines that has already been extended to 3D, and that uses fixed sparsifying basis like the Fourier basis. So we propose, from a sparsity point of view, to reconstruct our ultrasound signals from their sparse representation in a learned overcomplete dictionary, because this dictionary will permit a sparser representation of the signal, and this will be optimized for our class of ultrasound signals. And from a measurements point of view, we propose a 3D ultrasound specific subsampling protocol, which is the line-wise sampling of entire radio frequency lines. So we subsample beamformed RF signals, and this will increase the frame rate, and it will be easy to design in practice using existing acquisition systems. So this approach has already been validated in simulation, and now we propose to validate it on experimental 3D ultrasound data. So this would be a classical sampling pattern in 3D ultrasound images that is often used in compressed sensing. So you have a random sampling of a 3D volume. So here is the mask. And from an incoherence point of view, the reconstruction is possible, because then the sparsifying basis will be incoherent with the sensing basis. However, this would be inefficient from an acquisition point of view, because that would mean sending a beam in the environment and receiving it, and only afterwards subsampling this data. So that would mean the whole data was acquired and then subsampled. Or you can do analog to digital approach, but then it will mean modifying the acquisition system, which is now not our interest. So we propose a line-wise sampling that is adapted to 3D ultrasound acquisition system, scanning system. This is theoretically less efficient from a incoherence point of view, because the matrix here, the scheme here, is not random anymore, not as random anymore. However, this would be technically easy to implement on existing acquisition systems. And if you look at this example, so if imagine that you don't want to acquire this beamformed signal, so we subsample this beamformed signal. That means we don't acquire the equivalent raw radio frequency data. We don't activate the sub-array of elements, and that means that we don't send the ultrasound pulse in the environment. So this would increase the frame rate. And then from a reconstruction point of view, we use the blockwise compressed sensing reconstruction scheme, where we write the compressed sensing problem for each patch of our 3D volume. So here, X is the patch that you want to reconstruct, and Y is the 3D patch of measurements that we are supposed to acquire. And R is the line-wise subsampling matrix. And this is solved through the L1 minimization using a spectral projected gradient algorithm. So the reconstruction basis is of course the dictionary D that we learned from the 3D ultrasound. And then we compare this dictionary to the DCT and the Fourier basis. And again, since we're using classical acquisition system, the acquisition basis is the direct basis. Okay, so we acquired several ex vivo volumes, ultrasound volumes of 3 different organs. So we had 3 pig brains, 3 sheep hearts, and 2 sheep kidneys that were purchased from the store. And here in the table we have all the parameters of the acquisition. So these were acquired at the frequency, central frequency of 5 megahertz at the frame rate of 1 or 2 hertz. So we learned 2 types of dictionary. The first type of dictionary that we learned was an organ-dependent dictionary, where we trained our dictionary D with the K-SVD method on 2 volumes of two distinct brains or hearts. So here we learn a dictionary on the brain volumes and here on the heart volumes. And then we use compressed sensing reconstruction on a distinct brain or heart that weren't included in the training data. And then the second dictionary that we learn is a general dictionary, where we train our dictionary on patches that are coming from 3 different organs, so from 5 different volumes. So we learn the dictionary on brains, hearts, and kidneys. And then we test the compressed sensing reconstruction of this dictionary on 1 brain, 1 heart, 1 kidney that aren't included in the training data. So here we have the reconstruction results that compare the 3 sparsifying transforms, so the K-SVD in black with the Fourier and DCT in red and blue for the line-wise subsampling. And here it's in function of the number of samples that we remove from the data and is function of normalized root mean squared error. So as you can see, both curves of brain and heart have quite the same tendencies and are in between the same range of values. And the K-SVD for all the values gives a lower reconstruction error than the Fourier and the DCT. And of course, the error is increasing with the number of samples that we remove from the data. And then if we look at the reconstruction using the general dictionary, so this time we have a third organ that has the same tendencies as the 2 figures before. So again, the difference is high between the Fourier-based and the K-SVD-based reconstruction. And then if you look at the values of normalized root mean squared error that we get, we can see that the difference between these two dictionaries is minimal. It's only of 10 power minus 4. So we can reconstruct the same images using either the organ-dependent or the general dictionary. So if you look at the reconstructed images, for example, this is an image of the kidney volume of only one side. So here you have the Fourier reconstruction and the K-SVD reconstruction at 50% and 80% sampling. And then if you look at the Fourier reconstruction, we can see that we get almost the same results as K-SVD at 80%, while with Fourier 80%, we completely lose all the details inside the volume. And then if we take a closer look on a region that has many details, well, we can visually see that for 50%, K-SVD reconstructs well all the details inside the kidney, while at 80%, we start seeing reconstruction errors which are due to the blockwise method of reconstruction. So then we validated this approach in vivo experimental acquisition, where we imaged the liver of 4 healthy subjects and the kidney of 1 healthy subject. So we have here the parameters of this acquisition. So the central frequency was 4 megahertz and the frame rate was of 2 megahertz. So we have here the reconstruction of these in vivo images using the general dictionary that we learned on the ex vivo data. So the dictionary wasn't learned on the in vivo organs. So here again, the Fourier reconstruction at 80% completely loses all the details. And then if you look more in detail at the K-SVD reconstruction, we can see at 50%, the reconstruction is almost equivalent as the original image. While at 80%, we start seeing blockwise reconstruction errors. And if we look at the 4 dots, 4 structures here, okay, again, we can see at 50% we cover all the structure, while 80% we lose one here. So in conclusion, this approach shows promising results using the dictionary. The line-wise subsampling was feasible in practice, so it preserved the spectral details and large-scale structures. there's the generality shows a minimal loss in reconstruction. However, the limitation are the computation times, which are at 150 times bigger than the Fourier series. And so there we have a high overall computational time. So the perspective will be to implement it on GPU or in parallel implementations. And the second perspective would be to use the deep learning techniques, which offer the possibility to learn. Actually, the problem with the dictionary is that you don't have the inverse fast transform. So this might solve this problem, and because this kind of technique might learns the dictionary, but also learns its inverse decoder, so inverse transformation, and that this can maybe speed up a lot this acquisition.